Hello ladies and gentlemen, I am Dr. Claudia Albers, Planet X research and professional physicist, and today I'd like to bring to you another one of my articles, and it's entitled The Truth About Planet X and Cern. And in this article I'd like to answer the following question. Cern seems to be doing runs which coincide with the arrival of CMEs. Is Cern, with its huge magnetic field, augmenting our magnetosphere and thus protecting the Earth from CMEs? Now here we see Cern. Basically this is the LHC. This is the largest particle collider on Earth, and it stands for Large Hadron Collider, LHC, and it has a circumference of 27 kilometers or 43 miles. Now, I do not actually know if Cern is doing acceleration runs during CMEs because I have not looked at data enough to be able to tell. But I will look at the possibility of Cern being able to augment the Earth's magnetosphere. I know already that that's not likely, but I thought I would just put together some equations so we can get some numbers and compare. Now, the strength of a magnetic field can be calculated from the magnetic flux it generates over some closed surface. And the equation for magnetic flux can be simply, it's given by phi, which is B times A. B is the magnetic field and A is the area of that surface. But we can only use this equation if the magnetic field is constant over the area concerned. It's not constant, we have to do an integral. But I'm not actually going to go into that. I'm just going to use the standard equations that I already know. Now, the Earth's magnetic field varies between 0.25 Gauss and 0.65 Gauss. And so that means an average of 0.45 Gauss at the Earth's surface. And if we are considering only the Earth's natural magnetic field, we can consider it to be constant and thus estimate the magnetic flux it generates from this equation. So this would give us the flux for the Earth, the magnetic flux for the Earth, as the magnetic field times the surface area of the Earth. It's the surface of a sphere, so it's 4 pi r squared, and the radius of the Earth is 6,371 kilometers, and we're going to use the average magnetic field of 0.45 Gauss. And that will give us a magnetic flux of 2.3 times 10 to the 8 Gauss kilometers squared. Now, the LHC is essentially a toroid, so we're going to approximate it to a toroid. And a toroid is designed to have a very high magnetic field in the center, but the magnetic field is low on the outside. So the flux generated by it to start off with is supposed to be low. But since the magnetic field is so high, 8.3 Tesla, which is the same as 8.3 times 10 to the 4 Gauss, so 83,000 Gauss, we'll see what we get. So here's what a toroid looks like. It looks like a donut. It's got windings. Around it there will be current flowing in these windings, and that generates a magnetic field in the center of the windings. And we can see it here again. This actually illustrates the magnetic field that is generated. The magnetic field outside, as you can see, is very low. Now, the magnetic field of a toroid is given by this equation, mu naught Ni over 2 pi r. Mu naught is a constant, N is the number of windings, R is the radius from here to there of the toroid, and we can write the C over R. We C now is mu naught Ni over 2 pi. It's basically a constant. We need to know what it is, so I calculated here. C is B times R. We know B is 8.3 Tesla, and we know R because we know that the circumference is 27 kilometers, that the radius would be about 4.3 kilometers. So then we can calculate what C is, which is 3.57 times 10 to the 4 Gauss kilometers. So then we can calculate, or actually estimate, the flux produced by the LHC from the standard equation for the flux of a toroid of square cross-section. And that then is given by C, which we calculated here, times h. H would be the height of the toroid if it was a square. It's much easier to use a square, so we'll use that rather than a circular cross-section. So C is the height of the square, and B and A are the inner and the outer radius. And we can see what it is. B is the outer radius, so it's from the center of the toroid to the outer side of the toroid, and A is the inner radius from here to the inner side. And if we use that, and I think it's about, it's very low, it's about 10 centimeters in many places. I actually used I think 10 centimeters, yes, for the width of the toroid. And that will give us, that's 10 to the minus 4 kilometers. So if we plug in all the numbers, we get 8.3 times 10 to the minus 4 Gauss kilometers squared. And if we compare that with what we obtained from the Earth's magnetic field, 2.3 times 10 to the 8 Gauss, so that's an order of magnitude difference of 10 to the 12, followed by 12 zeros. So we can see that there's a huge difference between the flux produced by the LHC and the flux produced by the whole Earth. So there we can immediately realize that it cannot augment the Earth's magnetosphere. Its effect is way too small. So what exactly is the LHC doing? Well, the LHC is colliding particles moving at incredible velocities together in order to probe what these particles are made of and how they interact. However, it's a little more complicated than that, because if we understand that a particle is a wave packet of energy, and that the fundamental difference between a light wave and a particle is the fact that the particle is confined within a small three-dimensional volume and a small length of time. It's both three-dimensional space and time, so it's a four-dimensional universe that we live in. And then we should realize that space-time itself, the universe, the four-dimensional universe we live in, comes into what they are doing. So a particle is basically energy confined by space-time, and when Cern collides particles at extremely high speeds, they are breaking that space-time confinement. In other words, they are purposely trying to break the fabric of our universe, and thus most likely to break through an interdimensional barrier from our universe to another. And I believe this is extremely hazardous, as it could lead to the destruction of our universe, our reality, or our planet. Now, the work done by Cern and most particle physicists nowadays makes mention of the need to probe what particles were like at the beginning of the universe, after the Big Bang, in order to discover what causes mass. And this shows that Cern's experiments are not leading to any fundamental understanding of the universe we live in, because the Big Bang model has been falsified years ago. As I have written before, and that was in article 103, the 800 million solar masses black hole at the edge of the universe, the work of the astronomer Halton Arp, has shown that there are objects in the universe which are connected by dust and yet have very different redshifts. And that this makes the fact that the universe is expanding and started out in a Big Bang totally impossible. And this is an image from Seeing Red, Halton Arp's book. And what we see here is a Seyfert galaxy, NGC 7603, so it's an active nuclei galaxy. And it's connected by dust to a smaller companion. And the redshifts, the redshift of the galaxy is equivalent to a speed of 8,700 kilometers per second, whilst the redshift of its small companion is equivalent to 17,000 kilometers per second, nearly twice as much. So this would mean, according to the Hubble law on which the Big Bang model is based, that these two objects, this one is twice as far from the Earth as that one. But if they are connected by dust, that is totally impossible. Thus, this falsifies the Hubble law, and with it, the Big Bang model. And Holton Arp's work and his books are full of images similar to this, and careful explanations explaining why this the redshift connection on which the Big Bang model is based is wrong, and that redshift is actually an intrinsic property of matter. Now, in addition, I have written about the fact that the Planet X objects or stellar cores in the Sun's corona clearly show that we are not living in a gravitational universe, but in an electrical one, and that the interaction between these objects is magnetic. In addition, the gravitational interaction, as has been understood up to now, does not feature at all in the interaction between these objects and the Sun, as they are seen moving away from the Sun with CME material. And this is detailed in my article 67, Stellar Core Gravitation and Errors. And here we see one of these objects. This one was so large it was about the same size as the Sun, perhaps slightly larger. And this object, which is clearly a solid object, a stellar core or a very old star that has come into the solar system, has invaded the solar system, is now in the Sun's corona. Maybe not all the time, but it's often found. These objects are found in the Sun's corona and interacting with the Sun. And the fact that they don't collide with the Sun, but actually are seen moving away from the Sun with plasma associated with the CME, as this was seen moving away from the Sun, suggests that there is no gravitational attraction. The interaction between the Sun and these objects is electromagnetic, and the connection they make with the Sun is magnetic, and they actually provoke the Sun into having CME. So these are old stars. They've lost most of their ionizing material, their layers of material. So what's left is actually the core of what was once a main sequence star, and it's been exposed through going through the aging process, which takes them through the red giant and the white dwarf phase, and they are therefore old, burnt out stars, very little energy. They come to the Sun, they start absorbing energy from the Sun, they go through a rejuvenation process, which I have written about as well. Now, actually, while Cern particle physicists continue to ask what mass is and what causes it, I had already determined during my PhD research that mass is related to the electromagnetic interaction, which is mediated by the photon. So, in my PhD thesis entitled Electromagnetic Mass Splitting of the Goldstone Pion, I showed that the difference in the mass squared between the charged pions and the neutral pion was proportional to the fine structure constant. And the fine structure constant is a dimensionless constant which contains the charge squared of the electron. And that immediately shows you that the mass squared difference is proportional to the charge squared of the electron, therefore relates the two. And the fine structure constant, as I said, is equal to 1 over 137 in all unit systems. And the result I obtained was within a few percent of the experimental value, which is given here. So the difference in the mass squared, so that's the mass of the positive or the negative pion squared minus the mass of the neutral pion. It's given by 35.51 MeV squared. And in my thesis, I used the SU2 flavor version of the Nambu and Jonah Lucinio model Lagrangian density. and derived the gap equation, which I showed was equivalent to chiral symmetry breaking. In other words, this was equivalent to transforming from a massless to a massive phase. And the development of the gap equation was in many ways similar to what is usually done in BCS, which stands for Bardeen-Cooper-Schrafer theory to describe superconductivity, which can be explained as the coupling between phonons and Cooper pair electrons. Why this is of extreme importance is the fact that a phonon is equivalent to a fluctuation in the polarizability of an ionic medium in which electrons are moving. So superconductivity requires that two electrons be attracted to each other. But according to the electrostatic interaction, they should repel each other because charges of like charges repel each other according to the electrostatic or the Coulomb interaction. However, the attraction actually occurs because the two electrons are immersed in a medium or lattice made out of ionized atoms. That is, atoms minus the electrons. And these are positively charged and polarizable. And this polarizability means that the number of positive ions per unit volume can change. However, the positive ions move much slower than the electrons. So as one electron passes by, and we see here, so this would be the first electron moving through the lattice, and these are the ions in the lattice. So these are atoms minus some electrons. So they positively charge. So as the electron moves through, the positively charged ions are attracted to the electron. But the electron moves much, much faster than the ions can move. So by the time the ions have reacted to the presence of the electron and have become closer together so that they increase the density of positive charge in the area, the second electron comes along and is attracted to this region where there is a higher density of positive charge. And in a global view, this looks like the second electron is attracted to the first electron. And this is what is needed to explain superconductivity. Now, mass and the gravitational interaction are in many ways interchangeable, as I explained before. In Article 69, Planet X reveals that gravity is electrical. Gravity is actually a weak dipole electric force, much like London forces, and is also due to the polarizability of atoms within an object, just like the BCS theory Cooper pairs in a superconductor. So this means that the result obtained in my thesis using a similar treatment to BCS theory confirms that not only is mass and therefore the gravitational interaction due to the electromagnetic interaction, the gravitational interaction can be explained in terms of the interaction between electrons and positive ions or nuclei, or in other words, in terms of polarization within a material. That is due to the change in the shape of atoms due to some field, some electric field being applied to it. So in conclusion, Cern is not doing anything that can possibly be protective to our planet. If they are making runs during CMEs, it may be because the CME impact on the Earth's magnetosphere increases the chance of them achieving their ends, which seems to be the breaking of our space-time continuum, which is extremely dangerous for all life on Earth. In addition, Cern continues to lie to the world about the nature of the universe we live in, about the nature of mass, about the Big Bang model, and about their true motives in doing particle collisions. And here are my references. Here's my PhD thesis and Harp's book, which I've used, and the rest are articles that I've written about Planet X. This is Dr. Claudia Albers, Planet X physicist. Thank you for watching.